So you guys had 2018 FRQs for homework. I'm going to check your homework at the end of class. So what I want to do in class is this is the last day that I want to go over FRQs. I figure that I'm going to have help sessions each day. Before school, after school, and also during advisement. And I can use those periods or use that time to go over more additional FRQs if you want me to. But I think I want to just highlight certain FRQs from between 2016 and 2019. But I'm still going to be checking your FRQs each day until we're done. I think by Thursday we'll be done with all the way up to 2016. Okay. 2018. Sorry, 2019 was homework. Yeah. So I'm going to let me go over some of the 2019 FRQs. I think I got through 1 through 3, or at least parts of 3. So I want to highlight number 4. And then hopefully I can do like maybe 3 or 4 FRQs between 2016 and 2019. If you weren't here Friday, under your phones, there's the packet 6, which hopefully you guys have all picked up, and as well as the details and formula sheets for your AP exam. So if you haven't picked that up, you should see it at the top. Yeah, that's it.
What is packet 6?
Packet 6 is due whenever you're finished. Okay. Yeah, so you can wait till the last day of school to show it to me. But it is a required grade, and it will go in as a 100-point quiz grade. So it should be a nice grade boost. Okay, so I talked about how before, so we're on page 18 here, how related rates don't really have its own FRQs as much anymore, but sometimes we see related rates kind of built into a different problem. This is kind of half and half. This one has starts off with related rates, but then it ends with solving differential equations. So let me go through this here. A cylindrical barrel with diameter 2 feet contains rainwater, as shown in the figure above. And we got a cylinder here. The water drains out through a valve at the bottom of the barrel. So water level will be decreasing because water is coming out from the bottom of the barrel. Rate of the change of height with respect to time is modeled by dH dt equals. So we have a differential equation, a derivative equation that tells us how fast the height is changing with respect to time, where h is measured in feet and t is measured in seconds. Find the rate of change of the volume of water with respect to time, with the height 4 feet indicate units of measure. So anytime we see rate of change with respect to time, we should be at least have that idea that maybe this is going to be related rates. So with the related rates, we're going to be finding our derivative. Now, the nice thing about cylinders is that we don't have to worry about like cones with similar triangles, because if we had a cone, for instance, right, as the water level is dropping, the height is changing and the radius is changing, right? So we have 2 moving parts with a cone, but with a cylinder, if the water level is dropping, the height is changing, but what about the radius? Is the radius of the water level changing? No, it's staying the same, right? So the nice thing about cylinders is that once we know what the radius is, we can completely get rid of the variable, because that value is never going to change. So the nice thing here is, now that we know we're given what the radius is, which is 1. And Yeah, it says diameter is 2 feet, which means that the radius must be 1 foot. So we can go ahead and replace our r with 1, and we can simply just start with this equation. V is equal to pi h. Okay, find the derivative. V becomes dv dt, pi will stay, h becomes dh dt. All right, so now that we have our derivative, we can solve for dv dt because we know what dh dt is. That's given to us is -1/10 root h. And then we know once we've set our derivative in place, we can replace h with 4. Clean that up, we get -pi/5 cubic feet per second. Part B, when the height of the water is 3 feet, is the rate of change of the height increasing or decreasing? So we're asking if the rate is increasing. So we know the rate is already at the derivative, the first derivative level. Increase, decrease is going to take it down to the second derivative level. So we have to find the second derivative. Right? So rate of change refers to d2h over dt2. So we start off with dh dt. Find the derivative. We know this becomes d2h over dt2. We have to find the derivative of this, and then after that, we have to attach a dh dt because we're asking for h's derivative. So we go through power rule, -1/10 stays, bring down to 1/2, subtract 1 from the exponent, and then h becomes dh dt. Now, h is, well, I'm going to leave that h alone. dh dt, I can replace with -1/10 root h. I can cancel the root h's out. Negative times negative is positive. So that tells me that my second derivative is always positive. If my second derivative is always positive, then we know the rate is increasing. Okay, I'll briefly go over part C. Part C is our solving differential equation process. Use separation variables to find an expression for h in terms of t. So this is one where we don't have x and y's, but we have a predictable variable and a variable that we have we may not be as familiar with. But the idea is that if you're doing separation of variables, you know that t's on the left, h's, t's on the right, and then whatever the other variable is going to be on the left. So we want the h's on the left and t's on the right. Think of t as your x, think of h as your y. Right? So if I cross multiply here, I can get that dh dt lined up in place. The only thing that is really out of place is that root h. So we got to divide by root h to get full separation of variables. H is on the left, everything else on the right. We get that left side ready. H to -1/2 dh equals -1/10 dt. We go through power rule. Add 1 to the exponent, divide by the new exponent. -1/10. 1 becomes t. And then once we have our equation at the function level, then we can solve for c, solve for h. All right, so that's really what I wanted to go over from 2019. Let's see, number 5 is this method, washer method problem, cross section. So the only thing you got to worry about there is that we got to do this by hand because this is non-calculator. So use substitution, power rule, we got to do all that, show all that work. Number 20, page 20, there is need for product rule, spelling out product rule. And then part C, there's evaluating limit, and eventually it's going to turn into a L'Hopital's rule problem. Okay, so I want to highlight a few problems from 2018 to 2016. Let's go to page 21. And so this will be the last day of class that I spend class period going over FRQs. I'm still going to go over FRQs during help sessions. Again, help session every day, morning, afternoon, and advisement. Okay. Last push to get us ready for AP exam next Monday. Okay, so this is page 21. This is calculator active. This is another rate in, rate out problem where rate at which people are entering, rate at which people are leaving. So let's go through this problem. All right, people enter a line for an escalator at a rate modeled by a function given by R of t, where R of t is measured in people per second. So if it's rate in, rate out, you're always going to be given something that is a rate. So this is the rate at which people are entering into that escalator, number of people per second. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. There are 20 people in line at time t equals 0. Okay, so part A, how many people enter the line for the escalator during the time from 0 to 300? You know, part A is always going to be a little bit more straightforward, a little bit easier, just trying to get us into the problem here. So we know that we have the rate of our people are entering in. So if I want to find the number of people, I can just take the what of this rate. Antiderivative, yeah. So part A, just take the integral of from 0 to 300, between 0 and 300 seconds. You can write out the full expression, or you can just say R of t, dt. Make the calculator do the work for you. Make sure that you use x instead of t in your calculator. And this is not hard, but we do need to make sure that we're comfortable with our keystrokes in our calculator, being able to represent this in the proper form. So if we accumulate the number of people over that time period, we're going to get the number of people. Part B, during the time interval from 0 to 300, there are always people in the line for escalator. How many people are in line at time t equals 300? So we have rate in, rate out. So the idea that we got to take those three things into account, right? That the total number of people in line is, we have to account for that by considering how many people are in line to begin with, our initial, plus how many have entered, minus how many have exited. So total number equals initial plus now on the AP exam, you don't have to write all this out. Okay, I'm doing it just so that I can keep reminding us of the formula that I'm using to help build my equation. So I'm going to let P represent the number of people. Initial, what's my initial number? 20 plus, okay. And then the number of people from 0 to, I'm going to create a formula first. So I'll use R of x dx. R of x, R of t is the same thing. I just want to use x here so that when that t gets plugged in, it turns into a t minus, and then the integral from 0 to t, and then the rate is 0.7. It's a constant rate here. So it's just 0.7 dx. So this is a formula that we can use probably later on as well if they ask us about absolute max or absolute min. So now we can figure out the number of people at 300 seconds. Replace every t with 300. We already know what this number is, right? We can figure out this using the calculator. So math 9 from 0 to 300, 0.7 dx. So we get 20 plus 270 minus 210. Okay, part C is a little bit unfamiliar. Says for t greater than 300, so after 300 seconds, what is the first time t that there are no people left in line for the escalator? Because we know that after 300 seconds, there's no more people entering into the line. So however many people have entered the line by 300, we just have to figure out how long it's going to take for them to all exit the line. So well, the nice thing is we can bring in this number into our process, right? We know that at 300 seconds, we have 80 people. We have to figure out how long will it take 80 people to exit the line. So we know that there is a rate of 0.7 people per second. So we know that we want to figure out that 80 people. We know that 0.7 people per second. That means 0.7 people over a period of time, over a period of seconds. How long will it take for that period to actually reach 80? So we want to figure out how long will it take if it's 0.7 people per second, and then we have 80 people to account for. How long will it take before that clears? So 80 divided by 0.7, we get 114.286 seconds after 300. The part C is not really a calculus question. It's more just understanding that, oh, this is the rate. This is what we have. We have another 114 seconds to account for these 80 people to clear. And then, so that means after 300 plus this will be how long it takes before the escalator is completely empty. Part D, between 0 and 300, at what time t is the number in people at a minimum? So extreme value theorem here. To the nearest whole number, find number of people in line at this time, justify your answer. So we know that we got to test endpoints and critical points. To find critical points, we have to find p prime, set p prime equal to 0. So p of t is this equation. So p prime is just going to be r of t minus 0.7, because we know that derivative is going to wipe these integrals out. The 20 will wipe out to be 0. So part D will apply EBT. P prime, set p prime equal to 0, but first p prime is going to be r of t minus 0.7. Okay, any questions here how we got to p prime based off of p of t? So set p prime equal to 0. That's how we're going to find our critical points. So again, let's use that strategy of graphing and then looking for the x-intercept. Okay. The graph is going to cross the x-axis twice at 33 and 166. Okay. After we find those critical points, then we're going to test 0, 33, 166, and 300 all into the original P of T equation. Oh, and by the way, if we're trying to find that critical point and to make sure that we can see these values, we always want to make sure that we're comfortable with adjusting our x values. We know we're going from 0 to 300, so you do need to set your window from X min 0 to X max 300. Otherwise, if we don't have those values in place, then we're not gonna, if we go from 0 to 10, we're not gonna see these values, right? So just make sure that you're always comfortable adjusting your X min, X max, because they're always gonna tell you what your bounds are gonna be, right? So always just be aware that if you just hit a standard window, that you're not always going to get exactly what needs to show up. So make sure that if you go to window, that you can adjust your X min, X max. And you shouldn't have to guess what the bounds are. They should always tell you what the bounds are here between 0 and 300. Okay, so once we find those critical points, we take those endpoints and critical points, insert back into the original P of T equation. And then we just gather the number of people. 20 versus 4 versus 158 versus 80. The least number of people is going to be 4 people at 33 seconds. Again, I'm just highlighting some problems, but each day I'll be checking 6 FRQs. So tomorrow I'll check 2018, and then I'll check 2017, I'll check 2016. Let me see, what else? I want to highlight some problems that we may not be as familiar with. Yeah, I'm really wanting to highlight these rate in, rate out problems. Because we never took a test over it. So I want to just do as many as possible with those. So if you can go to, let's go to a 2017 problem, page 28. And this one is another rate in, rate out problem. How about let's do this? Let's try this for 5 minutes, see how far we can get. I'll read the problem first and then have you guys try, and then I'll go over it with you. All right, when a certain, this is a calculator active, this is number 2 from 2017. When a certain grocery store opens, it has 50 pounds of bananas on display. Customers remove bananas from the display at a rate modeled by F of T, where F of T is measured in pounds per hour. T is measured in number of hours after the store is open. After the store has been open for 3 hours, okay, let's keep that in mind. That's a key thing that we want to make sure that we keep track of. After 3 hours, store employees add bananas to the display table at a rate modeled by G of T. So for the first 3 hours, we have rate at which people are taking bananas off the stand as they're putting them in the shopping cart. But the replenishing is not going to happen until 3 hours in. Okay. How many pounds of bananas are removed from the display table during the first 2 hours the store is open? Okay, so part A should be pretty straightforward. Go ahead and try to set that up. Okay, part A is just math 9, definite integral from 0 to 2. Part B says find f prime of 7. Using correct units, explain the meaning of f prime of 7. Try that. Okay, so we can use math 8 with our f of x function. Plug in 7, make the calculator find it for us. This is our unit for f was pounds per hour, so we know f prime is pounds per hour squared. We get a negative, so we know that the rate is going to be decreasing, right? So the rate at which bananas are removed from the stand is decreasing by 8.12 pounds per hour squared. Part C is the number of pounds of banana on display increasing or decreasing at time t equals 5. So for part C, I want to build something first before I look at part C. I know that the total amount of bananas on the stand is 3 components, right? The amount to begin with, the amount that has been added to the stand, and the amount that's been removed. This 3 here is indicating that the replenishing is not going to happen until 3 hours after the store opens, right? 3 to 2. But part C is asking, is the number decreasing or increasing? So we're asking about a prime of t, right? Not the number of bananas, but it's a number of bananas per hour. So I'm going to build a prime. So a prime, we know a of 0 is going to be 0. The derivative is going to wipe out these 2 integrals. I'm just left with g of t minus f of t. So want to know, is the number of bananas increasing or decreasing? So I can find A prime of 5, which is just simply G of 5 minus F of 5. And this simply plugging this into our calculator here, G of 5, F of 5. These are already at the units that we need them to be, bananas per hour. So we just have to plug this in our calculator. Part D, how many pounds of bananas are on display at time t equals 8? So we can use this equation, plug in 8 for t. Yeah, the only tricky thing here is g of x is not from 0 to t. G of x is from 3 to t. So that can throw us off because when you realize that this g of x, that they're not going to put they're not going to add bananas to the table to the stand until 3 hours in. So these are staggered rates, right? These are not occurring at the same time, at least not for the first 3 hours. Yeah.
How do I know when to use like A prime or not? Like for the last, or like C and D? Like how do I know when to use it?
So I like to use, well, first off, part C didn't require this formula, but I like to use this formula as a starting point. Kind of feels like an anchor for me. I know that A of t is number of bananas, right?
Yeah.
I know that these have all been raised up to number of bananas. But see, if you look at part C, it says, is the number of bananas increasing or decreasing? So this part C, they want the rate to be bananas per hour, right? And because it's bananas per hour, I know I have bananas. So to get to bananas per hour, I got to find the first derivative. So A prime G of t minus N.
Why is D not? It's asking like bananas at time 8.
So part D says how many pounds of bananas are on display at time t equals 8. So now I'm back to asking for a number of bananas. So now I'm back to using this formula here. Yeah, so hopefully the units of measure will help you decide which formula that you want to use. So I'm just plugging in 8 in for A of t. So I know A of 0 is 50. Integral from 3 to 8, that's a calculator process there. I get 58 bananas have been added to the banana stand between third and 8th hour. And then between 0 and 8th hour, 85 bananas have been picked up or removed from the stand to add to for the customers removing them. So 8 hours in, there's 23 pounds of bananas on the table. Let me see. I want to do one more. Which one do we want to do? Okay. I remember this one was one that nobody liked when they took it. This is back in 2016. So I want you to read this one and just see if this makes sense to you. This is page 37. Not a fun one, but I think it's worth our time to just to kind of see like what curveball that we may receive on the AP exam. Okay, so number 5, this is on page 37. The inside of a funnel of height 10 inches has a circular cross-section as shown in the figure above. At height h, the radius of the funnel is given by r is equal to 1/20th 33 plus h squared, where h is between 0 and 10. Find the average value of the radius of the funnel. Average value of the radius of the funnel. Now, let me ask you this. Is this a cone? It's not a cone. And so I think that's what students were trying to do, use cone formulas but this is curved, right? This is not a straight line. So we got to think of this from a different perspective. And what is difficult is that we need to think of h as the independent variable and r as the dependent variable. So, and we want to find the average value of the radius. So what we need to do is this. Turning it sideways and understanding that h is our x and r is the y. And we want to find the average value of r. And that is, not an easy thing to just jump to that conclusion. If you're just reading this for a few minutes. So this is the way that we want to set this up. Okay. We want to think of, if I turn this sideways, that my h is my x value and my r is my y value. I want to find the average value of my radius. So my a and b value, average value theorem, my a and b value are 0 and 10. My r of t equation is 1/20th 3 plus h squared. And this is non-calculator. To add to the complexity, you got to do all this by hand here. So got to clean all this up. Distribute this through. We go through a power rule, plug in upper and lower bound. Now we don't have to clean up our answer. We just have to get into anything in this range will be acceptable. Yeah.
Did you have to add anything, or can you just know that it's like average value? Because it says average, so do you just like look at the numbers? Or did you have to like add anything with the?
What do you mean by? I mean, I knew that
like, just the simple theory, like just
it's average. Yeah, just average value theorem, right? But we do have to understand that my a and b value is 0 and 10. That's kind of hard because the way the diagram is drawn, it's not in the format that is most helpful to us. Part B. Find the volume of the funnel. Now, if we can get this to look like this, then finding the volume, does that make it easier here? How can we get from this shape to this shape? Take this and do what? Rotate, right? And if we rotate, what is that? What process is that? This method, yeah. And that's a tough one too, because if we don't have this frame of reference, it's hard to know, I'm just gonna take this and cover it up and think of it as a rotation to get from this to the shaded region. That's hard. That's really hard. But we know it's this method now that we have this in front of us. So top minus bottom, the top is sitting at the 1/20th 3 plus 3h squared. The bottom is sitting at the 0. And then once we get that top minus bottom, we can square our entire radius. Again, non-calculator here. So we have to FOIL all this out, clean all this up, plug in our upper and lower bound. Now, we don't have to get all the way down to these numbers because non-calculator, you can leave your answer like that. Just make sure you attach a pi at the end of your messiness. So as you can imagine, for this year, I think many students did not earn many points on this problem. It's just, if you can't get that part A, if you can't get that a lot of students were trying to do related rates, similar triangles, and that just threw everything off. So part C, it is related rates, but it's not related rates for a cone. It's related rates for this equation. So we got to do R becomes dr dt. We got to get dH dt to show up, and then replace dH dr dt with -1/5, and then we're solving for dH dt. Okay, so related rates, R becomes dr dt. 3/20th becomes 0, 1/20th h squared becomes 1/20th times 2h times dH dt. So I think many of us feel a little shaky with the related rates, but just to kind of keep in mind that if you see related rates, typically it's just going to be power rule. It's going to be relatively easy derivative rule, but we just have to keep reminding ourselves that, oh, related rates here, there's a hidden time variable, and that time variable is going to come out in the form of a d over dt, whether it's dr dt or dH dt, depending on what variable that they give you. So you just have to make sure you attach a d over dt once you've completed taking the power rule for that term. Okay, I want to go ahead and stop now, and I want to come around and check your homework, the 2019 FRQs. Page 15 through 20. I see you're good.
Only pass.
You showed me your thing.
Yeah, and then is it just like
Oh,
the
and
other?
then you have 2021 FRQs. Oh, page 15. Good, thanks.
And so you're just checking one after two a day?
Yep.
And then what about the other?
Other packet, just have to throw it in whenever you can. You have until it's easier. So you don't just turn. Answer on Friday, but grades are not due until the week after. Okay. Yes. You could make it almost about so I think tomorrow. Yeah. Okay, and then I'm also very well.
Not all of it.
I don't think that. Check it.
Like, I love my. Actually,
The PK comes. It wants to be having. Or something. Yeah. That's right, that's true, yeah. Hey, it's good. It's better for.
Honestly, never. And you know what? He gave me an 87 on that seminar, and I was the only person that talked, and I came in 6 sources instead of 4.
Let's try to summary it.
That was I yapped the entire time, but I was sitting back. I was he was like, "Oh, I looked at 40 bucks." So
I know, I got 80 on that. He's still putting the music video down.
he was like, "Oh, I love. Oh, I want to bring up a point that she made. She doesn't base. No, I didn't.
Did you specify which ones were like sporting, which ones were repeating?
Yeah.
Okay.
So I literally, I went through and highlight, I like, cleaned it out and I highlighted 2 different colors.
It has put in the music video, right? Yeah, no. It's put in the
Yeah, that put in my, my, the extra credit. 5 minutes, because I wrote that for the next one. There was, it could belong to any question on it. It was the only question on the page. The only question on the page.
I'll get the micro exam tomorrow. Yeah. Apparently, Mr. Green's gonna be there blasting like music for us as you go in, like both for both exams.